afternoon, everybody. Welcome back to DSP. Thank you for coming to the classroom on time. All right. So as I announced earlier, today is the day after midterm, and I decided that we can do 2 hours of lectures, sort of to make up for last week, because last week there was no class meeting because of the holiday. So we had to find another day to make up for that. Today will be one of the makeup lecture. So 2 hours. Hopefully we'll stay alive till the end. All right. So let's look at this on schedule to see if we are still on time. So just sticking to the plan, we have covered each topics in chapter 4 and chapter 5. You read the textbook. And chapter 5 is now for today. Yesterday was midterm, but for today we'd like to wrap up chapter 5 by going through that one last slide. If you remember from lecture 6, there was one last slide, which we didn't really have time to talk about it. So today we will wrap up chapter 5, and also then I'd like to straight head into chapter 7. Okay, chapter 7 is all about designing a filter, and I think that's the essential, most important skill you will learn in DSP. So we need to emphasize on filter design. Okay, that's the main topic, really the main difference between DSP and signals and systems, right? So you guys I assume that most of you, as I observe your solutions on the board, I know that you mostly have taken signals and systems. So to some of you, maybe a lot of the content in chapter 4 and 5 are actually reviewing signals and systems. Well, now I'm pretty sure that in chapter 7 we learn something new. We learn to kind of cultivate the design mindset, 设计的精神, all right? So we need to have that mindset of designing a thing to meet certain specifications. So about design. So today I have uploaded a lecture, an overview lecture, which is called lecture 7, 8, and 9 overview, right? So you can find it from from E class. Okay, please go download it if you haven't done so. Please do it. There's going to be an overview for filter design, which I'm going to share to you today. Okay, after we wrap up chapter 5, and then after, so we will spend at least 1 month, 4 weeks, starting next week. Actually, starting next week, or maybe a little bit of today, we will start talking about designing filters, and there are several kinds. Okay, several different methods. And then near the end of semester, I plan to mention just kind of touch base on a few special topics. And one special topic is adaptive systems, right? So difference equation, but how about we can make it adaptive to the environment or something like that? Yeah, adaptive systems. So which will be one special topic, and the other special topic I plan to talk about is information retrieval. Yeah. So signal processing nowadays is about AI. Yeah. You want the system to be intelligent. So is a filter that we are going to learn to design, is it intelligent? 是有智慧的吗? Maybe not really, right? Yeah. But intelligence means the system, yeah, that's why I want to touch base on retrieving information. Can we extract information from the signal that we record? Be it a video signal, audio signal, speech, music, biological signals, right? So we will probably near the end, near the last week, we will have that special topic. Okay, just kind of bridging the gap between DSP and AI. Okay, so that's a plan for this semester. And any question? Right? Okay, so let's switch to where we left 2 weeks ago, right? Two weeks ago, we were on this final slide of lecture 6. So let's slowly recall what was going on. Okay, what was going on? So at that time we spent a few hours just to solve this difference equation. Okay, this difference equation, as you know now, that the impulse response to this system with x being the input, y being the output, and this difference equation has a solution. I mean, its impulse response is the Fibonacci series. Okay, the Fibonacci series, because every present term is the sum of the past two terms. So it gives you the impulse, it creates the Fibonacci series as n increases, as time proceeds, right? And somehow the title, this is something that I do not recommend, by the way. This is just for the sake of making our discussion complete, okay? But the entire slide will tell you something that I do not recommend you to do. But it's possible if you insist, you can do this. Okay, so what's going on? We can let the time go backward. How do we do that? Just using this same equation, but in a sort of unexpected way, right? We can rewrite the equation from here to here. Is everybody okay with this? Just by inspection. This is the same equation, right? Absolutely the same equation, just moving terms around left and right. Absolutely, this is the same equation. And this equation is supposed to hold for all n, right? N equals to 1, 2, 3, 4, 5, and so on, right? But how about we let the time go backward? So if it holds for all integers n, so it should hold for n plus 2, right? Okay, so now evaluate this equation at the moment n plus 2. Then we have this. Then we have, just substitute n by n plus 2. You get this. Everybody so far so good? Substitute n by n plus 2. The equation should still hold, right? It's just another integer. N plus 2 is just another integer. But then we get this. I claim that this is equivalent to that. They look different, but they are equivalent. They're from the same equation. Or just, are we happy so far? So far, so good? Yes or no? Yeah? No? Is it strange? Is it okay? Yeah. But now, so mathematically, this is okay. But if you read this, if you interpret the way I write this equation with yn on the left-hand side of the equality and everything else on the right, so now it seems to suggest one line of code, right? This seems to suggest one line of code in which you evaluate y of n based on y of n plus 1 and y of n plus 2 and x of n plus 2. You can imagine this could well be a one line of code. Computer code, right? But then this is problematic. You see what I'm saying? So this means that in order to calculate y of n, we need future information. Because y of n plus 1 and y of n plus 2 is still not yet happening. It's in the future. So in a way, this equation, to implement this line of code, you need the time to go backward. And this is something that I do not recommend you to think further, okay? Because time just does not go backward. So mathematically, there's nothing wrong, okay? It's just not recommended, Because I think it can lead to a problematic interpretation in terms of programming, right? Because this line cannot be implemented. The future hasn't happened yet. Okay? It's going to be problematic, and in that the code requires the present output to depend on future output samples, these two samples, as well as the future inputs, one future input sample. So now this system is non-causal because the present is affected by the future. Okay? If you think of this as one line of code. Okay, So mathematically, there's nothing wrong. If you insist something wrong, if there's one thing wrong we need to point out is because it's perhaps that when we write this equation, it's not, the equation itself does not specify whether the time is going forward or backward. Let me say that again, okay? If you look at purely the mathematical equation of this line, this equation itself does not tell you if time is going forward or backward. Just by convention, by habit, by agreement, by our mutual agreement that we want the time to go forward. But the equation itself does not specify that. The equation itself allows time to go backward if you insist. Okay, if you insist. Yeah, I don't recommend, but if you insist. Okay, so, and this is why, like maybe in signals and systems, sometimes we say when you have a system function h of z, right? You probably learned a lot about h of z itself. Does not tell you whether this system is causal or non-causal. You still need to specify the region of convergence, whether it's inside the circle, outside the circle, or in between two circles, things like that. So all those issues will not be an issue if you don't do this. If you don't allow time to go backward, then there is no such issue. The region of convergence is always outside the circle. Outside a circle with the radius the largest, where you find the pole that is pole being the pole, right? The pole which is farthest away from the origin, right? So if we don't allow time to go backward, our life is so much easier. Yeah. Just if this is a unit circle with real part of z and imaginary part of z, and you find all the poles. Yeah. Some might be outside, okay? Yeah. Found the location of all the poles, and then the region of convergence for this z transform will be outside. Let's say this is the pole that is farthest away from the origin, far away from the origin, right? This is the most farthest one. So the region of convergence would be outside this large circle, okay? In this case. So there's no need for further clarification. We don't need to clarify, oh, are you talking about a system which is not causal? Because here we don't talk about non-causal systems, right? And I think the kind of the core problem, 那个核心的问题, the core issue right here is really when we write down a difference equation, it does not specify the direction of time. The time direction, going forward, going backward, is not specified. So that causes all the problems in here. But if we just stay with me, if you agree that we always interpret the equation, the way we look at it is to always allow the time to only go forward, then our life will be much easier. Okay? Will be much easier. Okay? So this is my comment, right? Regarding probably a lot of ideas here you learn from signals and systems is because of this, because of the equivalence of the two equations, and that's causing the problem. Okay, so any comment? Yeah. So one exception might be, in certain applications, time can actually go backward. When I say time cannot go backward, that means the real time, like real time, right? But if you are talking about the time index in a file, which you have already stored in your computer, and you load it and you want to process your file, then time can go backward, right? You can even play a sound file backward. You can do that, right? So unless we're talking about post-processing a file, then maybe you want this interpretation. But when we talk about deploying your system in real world and recording a signal and processing it in real time, then we don't need to worry about this. Okay? So it's a difference between whether or not you're storing the file and load it for post-processing, or whether you deploy your system in real world applications, in real time applications. Then that could be, there could be an exception. Post-processing, maybe you can allow the time to go backward. Fine. But that will make your life tougher when you talk about HZ transform and stuff. So in this course, we stick with a more simple idea. We confine our interest to only talk about causal systems. Okay? All right, so that would be actually the kind of final message I want to bring up for lecture 6. And just take on and think about this is fun stuff. Yeah, even though I do not recommend you to be too much worried about it. I will not test you on this idea, okay? But I need to mention that there is a lot of issues right here. Now let's take a 1 minute break. 1 minute break. You can, before we finally change our topic to filter design. In case you haven't downloaded the handout, please do so right now. It's available on EE class. I think certain professions require people to think of time, in the opposite direction. Some professions process time in the opposite directions. I think historians, for example, 历史学家, they look at the present and want to tell what's going on, what has happened in the past. Or 古生物学家, paleontologist, they dig out fossils. Fossils are dug out presently, right? But they don't want to figure out what happened millions of years ago. So if you have those applications, maybe tell me, right? Maybe apply signal processing, but let the time go backward. It is possible, right? But that will make your life tougher. So yeah. All right. So overview of lecture 7, 8, and 9, filter design methods. So let's go through slowly some of the categories of filters and filter design methods, okay? So to be exact, I didn't mention, but sooner or later you realize that when we say filter, that means multiplication in the frequency domain, okay? In this course, it means that we are multiplying a spectrum with a frequency response. That's filtering, okay? Multiplication happens in the frequency domains at every frequency. That's filtering. So which corresponds to convolution in the time domain. Okay, so that's how we define the word filter. Filter is to make multiplication in the frequency domain so that you are giving your signal a gain as a function of frequency. Multiplication gain is a multiplication. And phase shift, okay, because everything's complex valued. Those are 复数的. But with that, we will learn a few, two main categories of filters. One is IIR, the other is FIR, and it's very simple. IIR, I stands for infinite, F stands for finite. Okay, let's memorize it. Infinite impulse response, finite impulse response. IIR filters, FIR filters. So literally, the name suggests the definition. Okay, what is the definition of an infinite impulse response filter? That means the filter's impulse response lasts forever, okay? Lasts infinitely in time. Okay? Impulse, that's the definition of IIR. The filter will have a long, infinitely lasting impulse response. A finite impulse response means the opposite. Okay, if a filter has an impulse response with finitely many non-zero samples, okay, starting from time 0 and it ends at time 100, so that's a finite impulse response. If the length of the impulse response is finite, then we call it an FIR filter. So IIR means if you plot h of n as a function of n, then it can maybe last forever. Last forever. It may converge to 0. It needs to converge to 0 for stability, but it never really stops. The response can last forever, right? So that's infinite impulse response. And in contrast, FIR means if we plot the impulse response, then starting from time to maybe a finite length L. Yeah, the filter can have L plus 1 samples, but then after time L, everything is 0. We say the duration of this impulse response is finite. Therefore, we have the name. We suggest the name finite impulse response. Means h of n. Means there exists a finite length such that x of h of n is all 0 for n greater than or equal to L, something like that. Okay, so if you want to write down it to kind of translate my statement into math symbols, there's a finite length. Then after that length, or I should say, in this case, we assume causal. We do assume causality. Okay? But anyway, the idea is that the duration over which the impulse response is non-zero, that duration is finite. It's pretty easy to understand. Okay, so finite impulse response, infinite impulse response, right? So we look at some compare about these two different categories. These are, by the way, today's lecture overview is actually a summary. So maybe some of the ideas might not be clear, but this is sort of a preview. We just take a preview. So if something is not clear today, don't worry. We have one more month to talk about filter design. But let me just want to summarize to you that 先讲结论. I'll jump into the conclusion first. IIR filters are always implemented by linear constant coefficient difference equations. Okay, things like yn on left and with like linear combination difference equations. Right, I could not emphasize this enough. Right, IIR filters are always implemented by LCCDE. That's important concept. Whereas FIR filter, now we have a filter which has a finite impulse response. So practically, you would store all the sample values. Now, let me suggest that this is h of 0 to all the way to L minus 1 in MATLAB syntax, right? Just literally, what you would do is to store your filter samples in one array, and then convolve this array with your signal. So FIR filter is implemented through convolution. That clear? Because filtering is convolution in time and multiplication in frequency domain. So FIR filters, I will see, it always implemented by convolution. By storing all the sample values and then convolve. Whereas IIR filters, you cannot store all the samples because the duration is infinite. Okay, right? So it's not possible to store all the samples of IIR impulse response. You don't have the memory. Okay, so instead, you need to implement the system by difference equations, by something like yn equals to summation minus ak, you know what I mean, yn minus k, and so on. Okay, plus a possible linear combination with the input from 0 to n, bk, x, and minus k. Sorry if I run out of space. But this is one line of code. Okay, so you see the difference, kind of in terms of implementation. Okay, what you store here are the coefficients and past samples, up to m past samples, up to n past input samples. And of course, we store all the constants, and then you can implement the filter. Whereas in FIR is simpler. FIR, or you say, is just IR without this term, if you will. If we directly have yn equals to that, then that's FIR. Okay? These feedback coefficients make the impulse response infinite. Okay. So FIR versus FIR implementation. But one more thing to mention, this is also important. Turns out that the computation load, when we compare, the standard answer is that IIR, sort of the short answer is, the question is, which one is computationally more efficient? When we were designing a filter, a low-pass filter, do we use IIR? Do we use FIR? So there are pros and cons. 优点跟缺点. Advantage of IIR is it usually has a smaller computation load than FIR filters that meet the same specification. Okay, I will elaborate that. Specification 就是 specs. Usually IIR can lower your computation load, but there are exceptions. But the tricky thing is that FIR, if you implement convolution in the time domain, it could be not as efficient as IIR. But you can accelerate convolution by going to the frequency domain through fast Fourier transform. This is an important point that I'm not sure if we have time to address that in this semester. Okay, in my other graduate level course, I talk about that. Okay, accelerating FIR filtering by fast Fourier transform. Okay, FFT or FFT. So the debate goes on. Okay, whether or not which one is more computationally efficient. It's not a straightforward question to answer. It's not that easy to answer. Okay, but without FFT, definitely usually, without FFT, then usually IIR is more computationally efficient than FIR. Okay, without FFT, if you're not allowed to accelerate, then IIR usually is more efficient. Okay? It's more efficient to design than IIR. Save the earth, save the energy, save your chip area, save everything. IIR is usually more computationally efficient. So the next point, then it comes with a drawback. Okay? IIR has a drawback of having a non-constant group delay. Non-constant group delay, whereas FIR, in FIR we'll cover two different methods: window method, optimal method, and window method even has two different families of windows that we will cover: the cosine family and the Kaiser family. But we're talking about group delay. Okay, group delay cannot be constant for IIR filters. Whereas you will learn that the way we design FIR filters guarantee a constant group delay, which is a beautiful property. We will learn that. We will learn the reason why. FIR filters, after you design them, they are just simply because of the nature that the way we design FIR filters. These so many different ways, but every method leads to a filter which has a linear phase, which has a linear phase spectrum, or simply one adjective, 当作一个形容词的话, linear phase. We will have a linear phase design for any FIR method that we will cover. So what does that mean? So that means that if we go to the frequency domain, so that means that I'm just going to kind of casually draw a few pictures. Let's say we design a low-pass filter. Okay? Let's say we design a low-pass filter, and there is a spec that we want to have a corner frequency right here, a cutoff frequency, and then where below that is the pass band, and above that is the stop band, right? And then your IIR design may lead to a performance like that, and then the high frequency being pi. Okay, so that's your IIR design. And your FIR design may lead to similar performance, also a nice approximation. So your FIR design may lead to something with a ripple, and then maybe some ripples. But otherwise, it's also a low-pass filter. So negative response, if we just specify some requirement, both of them can meet your requirement for sure in magnitude response. So this is magnitude. and the IIR versus FIR in magnitude response. H, magnitude response, okay? But when you plot the phase response, the IIR phase response could, in general, will not be a straight line. In general, the phase response could be, I might be wrong, but just anything. I'm just randomly drawing something, okay? This is the phase response of your design. It's not going to be a straight line. This phase response will never be a straight line. So that's what I'm talking about. Okay, that's how I'm talking about this seriously. I'm pretty sure the group delay is what? The group delay, if you recall, is the slope of the phase response, right? And the slope is never constant. It's never going to be a straight line. Okay? That's what I'm talking about. Whereas in IIR, you can have straight line. Everywhere the slope is a constant, and or just for the time being, let me just draw a straight line. Seriously, I'm almost serious. This is what we are talking about: constant group delay, having a constant slope right here. Okay, with perhaps only one exception is when we have ripples. Sometimes the phase can change by pi. Don't worry about that for now. Constant slope, being more or less, every segment is a straight line. The phase spectrum of FIR signal, because of the way we design it, okay, we'll show. You will learn that the phase response will have segments of the same slope. Segments of straight lines. 就一段一段都是 straight line or segments of straight line. The reason will be clear. But today is just an overview. So don't worry if we are jumping between different ideas. Okay. All right. So drawback, we covered the advantage, computation load, IIR yes, FIR maybe not so good. Drawback, group delay, FIR good, IIR not so good. Okay. So that's a kind of short list of comparisons. Any comment? Okay, so in the next few slides, I'm going to give you a sort of preview of how we are going to learn IIR design. And the key idea is to borrow. 用借的, we borrow what? We will borrow from some existing, like pre-existing knowledge in analog systems. Now, historically, first people study analog systems, differential equations, right? Which has a lot of application in physics and mechanical engineering, for example. So analog systems existed way before digital systems. So historically, people borrow from analog knowledge. So there will be some analog, let's say analog low-pass filters, which have nice properties, okay? So we start with an analog. We will start with an analog system, an analog linear system, and you can talk about its transfer function in the Laplace domain. Okay, you talk about its transfer function in the Laplace domain, and then we will learn this technique. There is a technique called bilinear transformation. Bilinear transformation is a mapping between Laplace S domain and the Z domain, bilinear transformation. Okay, we'll learn that. So it's a mapping. Okay, so bilinear transformation can be written just generically as S is a function of Z, or Z, S being a function of Z. Okay, so we'll learn that. It's going to be a mapping between the two complex planes. One is in the S domain, the other is in the Z domain. And on this slide, I'm showing that it turns out that the way we define bilinear transformation leads to a nice property that the left half plane of Laplace domain correspond to the inside of the unit circle in the Z domain. And we will learn that. Okay? It's a very beautiful property. Okay? We have a transformation from S to Z, and the inside or in the opposite direction, the inside the unit circle is mapped, correspond to the left-hand side, left half plane of S domain. And this is important. Okay? And this is somehow important. S equals to, S is a mapping, S is a function of Z. Okay? So the idea really then, I don't know if I have this next slide. So, okay. So the left half plane is mapped to the inside of user. That's one thing. And also the boundary, look at the boundary. Yeah. The boundary of the left half plane is the imaginary axis, right? Right? The boundary, 这是它的边界嘛, the boundary of this region is the imaginary axis. Okay? So if you go bottom up on this axis, imagine you're going up along this axis in the S domain. Then turns out that after the bilinear transformation, you will be going around the unit circle. Okay? We're going around the unit circle starting from like way bottom there, around the unit circle in the counterclockwise direction. 反时钟的Let me repeat that. If you go up, it's equivalent to going counterclockwise in here. With DC mapping to DC, that's DC frequency, you know, in discrete for discrete time. DC map to DC and infinity map to pi. Yeah, so there is a map to this frequency. Yeah, frequency pi. So with that, we'll learn that it's actually a mapping, a kind of a transformation also between the two frequency variables, the big omega and small omega. Okay, bilinear transformation leads to a change of variable. It leads to a change of variable. It leads to a mapping between the two frequency variables. One is the big omega, the other is small omega. Okay, and that's what the next slide is showing. The next slide is showing you that actually there will be the bilinear transformation leads to this is a little small. I apologize for that. To this relation between big omega and small omega. It's going to be the relation of tangent. It's going to be the relation of tangent. Let me enlarge this. Let me copy this equation. The bilinear transformation because of this definition, because of that definition, turned out that it will lead to this relation between big omega with 2 over TD, TD being one parameter that we can adjust. Okay, this is one parameter that can be tuned. Okay, 去调整啊. Between big omega and small omega, so there will be this tangent relation. Or if you just do the opposite, omega is 2 times the arctangent of what looks like omega, that parameter divided by 2. Okay, or you can write that, whichever way you would prefer. It leads to this mapping between the two omega variables, the big one and the small one. Okay, big omega, small omega. There is a mapping. Yeah, and this is nice because this can give us a direct conversion from an analog prototype right here. I'll explain in a moment. This plot here is the frequency response of an analog prototype, prototypical filter in the analog domain, specified by its frequency response with big omega being the variable. Okay, but now after this change of variable, then we have equivalently, or it leads to a filter with small omega being the frequency variable. So we begin with the prototype, and then we can obtain a design of a digital filter. So that's the kind of the idea. Okay, idea is to borrow from analog, and then make it digital. Yeah. So that's a way, kind of tricky but interesting way to design a digital filter by starting with analog, okay? So we'll spend at least the next week to focus on what's going on, to focus on what exactly is bilinear transformation, and then why does it lead to this change of variable. Yeah. So do you know how to read this? So this is like, if you look sideways, right? This is gain versus frequency, okay? So that's a pass band and stop band and so on. And then if we just map every big omega to a small omega, okay? And just because of or the opposite. So if you take, for example, pi, plug it in, it maps the tangent of pi divided by 2, which is infinity. That's infinitely far away. Now, can you read this? Now, we'll repeat it, okay? We'll repeatedly showing this. But this is the way we read it. Just every omega, big omega corresponds to a small omega, and so and vice versa. One-to-one mapping between big omega and small omega, which can be thought of as a change of variable, change of the frequency variable between big and small omega. Okay. Okay. So enough of IIR. So let's now talk a bit about FIR. Okay, yeah. Before we head to the break, yeah. Now, for FIR design, we do not start from analog. Okay, I promise you. Actually, it's easier to design FIR. Okay? In my opinion, FIR is easier to understand. So everything now is discrete time. Okay, no need to worry about Laplace or continuous time, right? So now to design the FIR filter, we just again using low-pass filter, ideal low-pass filter, using low-pass filter as an example. Okay, so let's begin. For example, for this example in homework 2, if you recall, in one of your homework, problem 1, you have seen this impulse response, the sinc function. Right? We've seen it all the time. Okay, there's a sinc function which can be defined as sine of a cutoff frequency times n divided by pi n. Okay, when n is not 0, and we need to separately define what happens when n is 0. Okay, using L'Hopital's rule or else. So we have seen that this is the impulse response for an ideal low-pass filter with a cutoff frequency at exactly that. So let me use here. Use this space. Just to recall that this is something we have done for one homework. In one of your homework. In one of your homework, we were already thinking about. I remember in that homework, I first gave you this. I gave you something like a frequency response in one of your homework. Okay, you can just check it. If we specify that there is a discrete time spectrum, there's DTFT. Let me say, if this is a DTFT of something, okay, if this is a DTFT of something which is uniform for within this frequency range, and 0 unity, which is 1 within this range and 0 elsewhere, okay, from here to pi, from here to minus pi. So this is in that homework. If we have a G Ej omega that's defined as being 1 when omega is smaller than omega cutoff, and 0 elsewhere when, let me just play safe. Omega cutoff smaller than omega smaller than pi, okay? If you have this spectrum, then the inverse DTFT of it corresponds to an impulse response. Okay? If this is a system, if G is, if you take the inverse Fourier transform, then you can obtain that result. Okay, just using the good old definition of inverse Fourier transform, you can obtain that. You can obtain exactly that. The inverse Fourier transform of this, low-pass filter is a sinc function in time. Okay, So it doesn't hurt for us to again draw a sketch of the sinc function. Okay, let's try it. Yeah, let's say the sinc function has now we know that it has sort of an envelope like that, I need more time for in the negative direction. Yeah, zero crossing, that's an envelope. Okay, sinc function extends infinitely on both sides, right, to the left and to the right. So that's g of n. With the top right now being omega c divided by pi, that's the top sample, and then so I'm this is just a sketch, okay? It's just a sketch. G of n, and similarly, it's going to be symmetric. So you know what I mean. So this is really G of n, how G of n looks like, and it extends infinitely on both sides. So at one point I mentioned to you that ideal low-pass filter cannot be implemented because in time you need infinitely many samples. Okay. All right. So G of n extends out to both sides infinitely, but then how can we kind of if we cannot store everything right here, how about storing just the middle part? Right. Just practically, you cannot store everything right here, okay? So how about we just store the middle part? Let's say, let's say this part is maybe I only need so much. Yeah, maybe this is from minus n can be big, and it can be 200, 56. All right. So let's store the middle part and then just forget about everything else here. Set everything else here to 0. That's one idea, right? If we cannot store, it's not possible to store everything right here. So let's just do the best we can, see how much memory do we have. Store just the middle part. From time minus n to plus n. N can be big, but n will be finite. Okay, so far so good? Everybody with me so far? Storing just the middle part. And I claim to you, this is great, in my opinion, this can already be called a design. Okay, so don't think of design being a hard thing. Design sometimes is just from intuition. If you cannot store everything, how about storing as much as you can? Oh, 这个图没有画很好。Anyway, how about storing just the middle part? And I tell you, this is not a bad idea. Actually, this is really not that bad. And I actually would like to call it a design. It's already a design, right? Because you put your mind, you think about it, right? It's already your design. Great. But we can certainly do better, okay? And that's what we need to learn about FIR processing. This is a very naive design, but actually its performance is not that bad, okay? Call it design, fine, but we can do better, okay? So that's why we need to talk about, spend maybe at least 2 weeks, maybe 3 weeks to talk about how to get better from here. Okay, I come to that this is already a design, but we can do better by shaping your result. Okay, so idea is how about we will multiply this middle part with a window function. Not filtering yet. This is still in the design process. Okay. We're not applying the filter yet. Okay, we're still designing the filter. But the way we design filter is by multiplying this middle part. Okay, this middle part, multiply it with a window function. Let's call it W of n with subscript ZP, which stands for zero phase. Okay, zero phase. The reason will be clear. We'll multiply this H of n with a kind of a smooth function, smooth window. Okay, window function. Okay, so next slide. And so this is so let's take a break. So when we return, I'll tell you about this. Okay, let's take a 10-minute break. So now, back to FIR, finite impulse response. We start from the ideal low-pass filter. Using low-pass as an example, of course, you can design low-pass, you can also design high-pass. Okay, but we're spend time on low-pass design because you know one thing, you know the other thing, right? So low-pass design for FIR filter, we begin from looking at the ideal response, which is infinite, and you don't have that space to store everything. Okay, so we need to truncate. This is truncation, 截断, truncation. We need to make a truncation first. Yeah, we need to just sacrifice everything here. Just if they are small enough, maybe by chance we can ignore them. Okay, without incurring too much error. Okay, just focusing on the middle part. Or I claim to you that already just by storing the middle part, then you have a finite length. Okay, and there's one issue about causality, by the way. Okay, so here the time goes from -n to n. Okay, so strictly speaking, your design is not causal yet. Okay, your design is not causal, so you need to make a shift. Okay, so your final design might be something like, let's make h equals to g of. We want to shift everything to the right. H equals to g of n to the right, shifting to the right, n minus n. Then we say this is your a design. Okay. So if this is g of n, then the time 0 should be right here. For h of n, the time index runs from 0 to n. Okay, by simply applying a shift, then you have now h of n officially it becomes a causal filter. I claim to this is already not a bad idea. This is not bad at all. Okay? Not bad at all to just truncate and shift. To make a truncation and then shift. It's not a bad idea, but we can do better. Okay. The way we try to do better is to multiply h of n with the window function. And on this slide, we're looking at a few commonly used windows, so which is denoted by w of n. Okay, by w of n, wait, shifting to the right, I'm struggling, and that's right. Okay, okay. So this is a window function, and there are a few different kinds. Actually, the rectangular window is all one from 0 to up to m, where m here is 2 times n. Okay, so imagine that truncation itself is just this that corresponds to using the rectangular window. Don't change the shape yet. But for these 4 additional windows, they have different shapes. All 4 of them have different shapes. With middle being the top, and like for example, there is one called Hamming, there's another one called Han, and there's another one called Blackman. And they all look like bell-shaped. 就像中型的 bell-shaped. Okay? And there's the 4th one, which is not that important in my opinion, but you can also define a window by a triangle. By pulling a straight line from 0 to the middle. There's a straight line, right? And that's also one possible window to use. So the idea is that now we are going to multiply h of n with w of n. Okay? That's the action of windowing. We're going to multiply h of n with the window function. Or do I left my green chalk? This one, So we will multiply h of n with, let's say, the triangular window. Okay, for example, we multiply it with the Bartlett window like that. You'll be multiplying the triangle sample by sample with your design. Okay, hopefully to improve the performance. Shaping with the window function. That's a shaping. That's a shaping. So then if this is your w of n, so your final design, your improved design might be this. Your improved design might be h, let me say improve of n equals to this naive design h of n simply by truncation times a shaping function Wn, okay, which has the same length. You can try that, yeah. So much of our lectures will be focused on analyzing the performance. Okay? Analyzing performance. So the next question is, when we multiply our truncated impulse response in time with a shaping function called the window. Okay, multiplying your truncation with the window, what will happen back in the frequency domain? Will happen back in the frequency domain. So yeah. So in general, we know that your frequency response will be low pass but not ideal. Okay, it will be low pass but not ideal. Okay, so in the next slide, we are going to talk about how do we evaluate the performance. Are there some performance indices for us to look at? All right, so far so good? So back to the frequency domain. This might be your design. This is the result of your design, okay? The actual magnitude response is not ideal anymore. It's not ideal anymore. So let's say we want to so this is what we are looking at right now is a tolerance scheme. Okay, tolerance. This is called a tolerance scheme, and we'll explain. So there is a pass band and a stop band. Okay, but here we also allow a transition band. Okay, you define the corner frequency omega p, the edge frequency 边缘的 the edge frequency for the pass band right here, and also you define so you're allowed to make transition. Your filter is allowed to make transition from pass band to stop band. And in between, this is called the transition band, where the gain drops from nearly 1 to nearly 0. Okay, there is a transition going on right here. Pass band, transition band, stop band. Okay, and see here you're looking at this frequency response. In general, it's not going to be exactly 1 inside the pass band and not exactly 0 in the stop band, because the performance will not be ideal anymore. Okay? After truncation, after shaping, right? The performance is not ideal anymore. So we need to evaluate how much does the performance deviate from ideal. 它离那个 ideal 差多远呢？how much are we allowed to deviate from the ideal response? Okay, and that's called the tolerance. How much error do we tolerate? Okay, how much of the gain are we tolerate to deviate from 1? So maybe if the gain, even though it's not exactly 1, but if in the pass band is bounded up and down between 1 plus delta P1 and 1 minus delta P2. So that's the tolerance we're talking about. Delta P1 and delta P2 are called the tolerance, pass band tolerance. Now we tolerate the response to be in between, in this interval, within this interval. If the gain is within this interval, then we say, okay, that's fine. You've satisfied my specification. Okay, I'll accept it. Okay, that's called the tolerance. On top and at the bottom for the pass band, the pass band tolerance parameters, 2 of them. And similarly, we have stop band tolerance parameter denoted as delta S right here. Okay, how much are we allowed the stop band response to be non-zero? It cannot be greater than this. Okay, the gain should not be greater than this, what we are willing to tolerate. 1, 2, 3, 3 tolerance parameters with you also specify the cutoff frequency or the edge frequency for pass band and the starting frequency of your stop band to be somewhere greater than at a higher frequency than that. Okay, so that's the tolerance scheme. And then with these terminologies, now we can talk about how we want to specify our design goal. Okay, what will be our design goal? For FIR design, we have a trade-off between a few parameters. So usually, if you aim for let's say, usually there's a trade-off between how narrow the tolerance is and how narrow the transition is. Okay, let me repeat that. There are like two competing goals. Yeah, there really are two competing goals. To reach ideal response, you want this ripple to be small, right? These are ripples. Yeah, 涟漪嘛. Yeah, so these are ripples. You want the ripples. You want the ripples to be controlled, to be small. Okay? There will be ripple, but you want them to be as small as possible. You want to suppress the ripple. Also over there, that's one ripple. Okay? You want to suppress the ripple while making the transition as narrow as possible. Okay? Because ideal filter has no transition. In ideal filter, the pass band and immediately the stop band. The transition is so sharp. Right? That's ideal. That's what we call an ideal filter. It's black or white, either pass or fail. Okay, and there's no transition in ideal filter. But when you truncate the ideal impulse response, we know that when we go back to the frequency domain, the magnitude is not going to be ideal anymore. The magnitude will be different. The magnitude response now has a transition region, okay, and some ripples right there. So, yeah. So on one hand, we want this transition to be as narrow as possible. And on the other hand, we also want to suppress the ripple. Turns out that these two factors are competing. These are competing goals. These are competing goals. So every time we talk about, for example, one kind of window, then we need to evaluate then what would be the transition, what would be how good is your ripple control, and how fast is your transition, okay, from pass band to stop band. It's two competing goals already. Yeah. So we'll cover that. So for this method of designing FIR filter, we will evaluate all the performances, okay, using such kind of tolerance scheme. And the next topic that we will cover is yet another way, a different, should I say, a completely different way of designing FIR filter. Okay, and here it's called optimal FIR filter design. Okay, and in this method, we now start from sort of a more abstract formulation. 这个整个的架构啊 the entire formulation is now made more abstract, 比较抽象一点. But let me try to explain it to you for the first time. So we can specify filter design as a minimax problem, minimizing the maximum of something. Okay, sounding really cool. So we want to search, like find design. This is our design. A filter is FIR, right? So FIR filter is a vector, if you will. It's an array of L+1 samples, L+1 unknown samples. So you can imagine that you have a space, sort of a space of H0 being the first dimension, H1 being the next dimension, H2, a multiple dimensional space R to the L+1. It's a search within this space. Any vector that minimizes the maximum performance deviation, right? So that's called optimal design, right? The entire framework can be stated as a minimax problem. Finding your design in that space, in the space of L+1 dimension, such that some kind of the maximum error is minimized. Right? So we'll cover that. That's the kind of our last topic for filter design. Please expect that. We'll enter this kind of thinking. Okay? We'll be using this kind of thinking, formulating design as a minimax problem. Minimizing what? Minimizing the maximum error function. And the error function is itself as a function of frequency. This is complicated, right? So in this way of design, I just tell you, this optimization process requires some interesting knowledge about polynomials. Turns out that We will be applying what is called an alternating theorem in polynomial theory, 多项式的啊, and the kind of polynomial we're working with is called Chebyshev polynomial. And Chebyshev polynomial does not look like a polynomial at first. Let me explain. Chebyshev polynomial T of n, the nth order Chebyshev polynomial is defined as cosine of n times r cosine of x. Yeah. It's actually a polynomial for any integer n. This is kind of interesting. T of, yeah. Oh yeah, just go home and you have 1 month of time. Okay, we'll explain like these are actually for any n. It gives you a polynomial. Cosine of n times r cosine of x is a polynomial of x. Think about that. It's actually not that hard once you see the trick. And we will be using such kind of polynomials in order to construct our optimal filter, okay, to talk about optimal design. So as I said, this is just an overview, so don't be afraid, okay, if things look scary. Yeah, they are. But we can take it slowly. We have 4 weeks. After today, we have 4 weeks to talk about filter design, all right? Any comment? Any comment? All right, so that's an overview. Yeah, did you have a comment? No, you're 手举一半. Things are exciting right here. Okay. So next Wednesday when we come back, I have this half-finished lecture, and I can show you. So next week when we come back,